Okay, students, let's talk about precipitation. So if we have something that is going to precipitate. So in our last example, we knew that we could only dissolve, 1.21 times 10 to the negative fifth moles per liter in our solution. If we were to add any extra than the solubility, we would end up getting a precipitate. So a precipitation occurs when the concentration of our ions goes beyond our solubility limit. Our solubility, right, is our KSP. So if our Q value, so remember how our Q is when we are not at equilibrium, K is when we are at equilibrium. So we can compare our K to our Q value. We know that our K is going to be when our solution is completely saturated. So when our solubility is at its highest, we solve for the solubility, we figure out that we do not have any precipitation. So if our Q equals our KSP, then our solution is saturated and we will not have any precipitation. If our Q is less than our KSP, that means that we can add more of our solid salt until we end up getting a precipitate. So if our Q is less than our KSP, we are unsaturated and we will not have a precipitate. If our Q is greater than our KSP, then we have gone beyond our limit of saturation. And so therefore we will be above saturation and we will get a precipitate. Some solutions will end up having a Q greater than a KSP, but we won't see that precipitate until we disturb it. So that would be a supersaturated solution. Remember, that's something like a hand warmer. Hand warmer is a supersaturated solution until you go ahead and break the little piece inside. It will stay supersaturated, but once we disturb it, it will then become a saturated solution. Remember, things will fall out of solution. So here on the left, there is a solution of silver nitrate. If they add some sodium chromate to this, you will end up getting a precipitate. So we will get some precipitate coming out. So in this case, we know that our Q is greater than our KSP because we have a precipitate. In something on the right, if we had a supersaturated solution, you can see that this middle picture of the supersaturated solution, we don't know if our Q is greater than our KSP unless we disturb it. So in this case, they added a seed. What ended up happening was that disturbed our equilibrium, and all of a sudden we end up getting this solid sodium acetate forming. So this one did have a Q greater than the KSP. We just couldn't tell that until we ended up adding a seed crystal. So here's a problem. Let's see what this looks like. We have some solution. It contains lead 2 nitrate, and it is mixed with sodium bromide. We end up getting a solution that this solution contains 0.0150 molar lead 2 nitrate and 0.00350 molar sodium bromide. Are we going to get a precipitate in this new solution? Well, what should we do? Will we get a precipitate? So we actually need to look back at last semester's table. So remember this table, 8.1? First, we need to figure out, are any of these going to precipitate? So our possible products, let's take the sodium, right? Our sodium, our cation, is going to mix with the anion of the lead 2 nitrate to give us sodium nitrate. If we look at the right, we see nitrate. Every single nitrate is soluble. Remember, there are no exceptions. So if you need to look back at this chart, figure out how to read this chart again, please do. But sodium nitrate is always going to be soluble. Our other product we could get is our lead is going to combine with our bromine. So we're going to get lead 2 bromide. Lead 2 bromide, let's see. Well, it says bromine. Okay, bromine looks like it's generally soluble, except when we look to the right, when paired with these ions, and lead is there. So therefore, lead 2 bromide is not soluble. Once again, we said technically that doesn't mean it's not soluble. It's only very, very insoluble. So some of it will be soluble, but most of it will not dissolve. So that means there is going to be a KSP value. So we would need to pull up our KSP chart and figure out what the KSP is. So the KSP of lead 2 bromide is 4.67 times 10 to the negative 6. Great. So now we know what we're looking at. So we're going to be looking at the lead 2 bromide. That's the only one we're going to focus on. That's the only product we care about, right? Because the other one is completely soluble. So what we can do is we can go ahead and write a Q expression. So Q is the same as K, right? It's just when we're not at equilibrium. So our Q equals our lead 2 plus times our bromine, right, squared. So our Q, we would plug in what the results are. So they told us our lead 2 plus, they told us the initial concentration was 0.0150. So we're going to plug that in. Our bromine, we're also going to plug in the initial concentration, and that is going to be raised to the second power. So that should be an exponent. We go ahead and solve that Q value. We get 1.84 times 10 to the negative 7th. We compare Q to K, right? So our KSP was 4.67 times 10 to the negative 6. This Q number is smaller. So our Q is smaller than our KSP, and therefore we are not going to get a precipitate. So we can figure out, are we going to get a precipitate by comparing our Q to our KSP value? What we can also do is we can selectively precipitate out things. If we want to only precipitate out one thing or another, we can do that. So if we have a solution that has several different cations, we got a bunch of cations, right? But we only want one of those cations to come out in solution. We can add some reagent that will form an insoluble salt with the one ion we want, but not with the other ones. We call this a selective precipitation. A successful reagent, so one that is going to precipitate out, we need it to precipitate out with more than one of our cations, depending on what we're looking for, as long as our KSP values are significantly different. So what we end up getting is, here's an example. In this solution, so we have some seawater. We went to the ocean, we got some seawater. We have in our seawater magnesium and calcium. They told us the concentrations. They can be separated by selective precipitation with KOH. So what is the minimum amount of hydroxide that triggers the precipitation of magnesium ions? So we only want magnesium ions to come out. We do not want the calcium ions. We only want the magnesium ions. So what we need to do, we need to write the magnesium hydroxide expression, because that's what we want. We want our KOH, right? We want the hydroxide to combine with the magnesium to give us a precipitate. So we're going to write our Q equals magnesium times our hydroxide raised to the second power. We plug in our magnesium concentration because that's what we need to precipitate out. We need to precipitate out 0.059 molar magnesium. We know we'll get a precipitate when our Q equals our KSP. So we need to look up the KSP of magnesium hydroxide. We would see that it is 2.06 times 10 to the negative 13th. And then we can solve for the concentration of hydroxide. So our concentration of hydroxide has to be 1.9 times 10 to the negative 6 molar in order for us to precipitate out our magnesium. If it is less than that concentration, our magnesium will not precipitate out. It has to be at least 1.9 times 10 to the negative 6 molar. Stay tuned for our next video.